Hello CRO world, and welcome to another installment of Chemical Engineering Design. In this lecture we will cover an example of the procedure used in the design of control valves. Now in the following process we are required to design a control valve to meet the flow rate specifications as shown, with the volumetric flow rate at 1.2 meter cube per hour, which is pretty low. We are also required to specify a pipe diameter, as this has not been specified to us yet, but we have the wall thickness of 5 millimeter that is given to us. Perhaps we calculated a required wall thickness. We found that the corrosion factor was 3 millimeter, and the rest of the requirements to maintain the integrity of the pipeline was equated to maybe 0.7 millimeter, which was rounded off to 1 millimeter. So 1 millimeter plus 3 or 4 millimeter will give us 5 millimeter. Okay. Yeah, so generally it depends on the process. The corrosion factor is really going to be quite substantial, so between 3 and 4 millimeter. So let's just say that we've rounded the calculation for the wall thickness to be 5 millimeter. So first off, in this design we determine the available total pressure difference, variable pressure difference for the system using the mechanical energy balance. Now the total variable pressure difference is all the pressure differences, including the control valves pressure drop, and excluding the static differences, which pertain to the endpoint pressures, as well as the elevation, which do not and typically cannot change. So remember, an existing process is a physically constructed process containing large vessels which can hold up to 50 million liters of reagent or liquor or whatever you're treating or using, and these typically cost millions if not billions of rands to construct, including the civil engineering aspect of laying concrete down, installing steel structures, etc. And the process itself has to operate at the required endpoint pressures. So you cannot just change an elevation or a pressure inside of a reactor or a distillation column or flash drum, or else the process or the entire plant may not operate economically anymore or may not actually run at all. So that being said, the total variable pressure difference is the only part of the process which can actually be altered or changed. And for this process it is calculated at 619 kilopascal. This is what is available for the control valve to utilize, but obviously the control valve cannot utilize everything. So next what we do is we determine the design flow rate, because this is going to be used in the design of the control valve, and this is specified from the normal flow rate of 1.2 meter cube per hour. So since this is perhaps a normal process, then the design flow rate will be 15% greater than the normal flow rate at 1.38 meter cube per hour. Next we choose a suitable pressure drop across the control valve at the design flow rate, which should fall between 25 to 50% of the subtotal variable pressure difference, which is equal to the total variable pressure difference minus the control valve's pressure drop. So let's go over a few of the options that we have available, since we have to consider the energy that we have available to us. We shouldn't be too wasteful or too lenient with using up some of this energy. So what generally happens is, for example, you'd have a pump. In this case we have a high enough endpoint pressure difference to drive the flow, but if you have a fluid mover, in this case the fluid mover would add a bit more extra energy to the system that's not actually required to meet the flow rate, and we would use that extra energy in our control strategy. So here we have the following options given to us, and we need to then choose a conservative choice. The upper limit might result in too much control for the control valve. In other words, the control valve just uses so much energy that it's just very wasteful. While the bottom limit may result in too little control, the control valve would be open too much, and it would simply not be able to control the system adequately. So let's go with this option, since it does not use too much energy for the system, but is also not too small either. The larger option of 0.4 kPa is slightly more wasteful than the selected option here. Now, how do we determine the subtotal variable pressure difference? Well, we know that the sum of the subtotal variable difference and the pressure drop across the control valve equals the total variable pressure drop. And we can substitute in our selected pressure drop that we've chosen in the previous slide over the control valve into this equality. Since we have two equations and two unknowns, we can reduce these to one equation with one unknown and solve for the subtotal variable pressure difference, and this gives us a result of 476 kPa. Next, we calculate the pressure drop due to the friction so that we can select a suitable pipe diameter. Since the process, the way that the process has been set up, we would actually not have any differences in kinetic energy. The difference would be zero, assuming that the pipe exit at the top of the column hits the fluid that is inside the column and stops the flow. So therefore we don't have any kinetic energy difference here, which makes our calculation a bit easier. So the frictional pressure loss is equal to the subtotal variable difference, pressure difference in this case, and therefore we can calculate a theoretical pipe diameter of 11.5 millimeter. Now remember, this is a calculated value. We now need to select a available nominal diameter that closely matches this result. We can either choose a nominal pipe diameter of 15 millimeter, or we can go with 20 millimeter. But 20 millimeter might be slightly too expensive, so we first test the 15 millimeter for now. We use the real pipe diameter, the chosen nominal diameter available to us again, just to check the frictional loss so that it doesn't end up being too big or being too small. Remember, we have only a certain available energy difference that we can utilize here. And we obtain the following result for the designed pressure drop due to frictional losses of 973 kilopascal. Now this is much larger than the 476 kilopascal that we require. And so for the system we should try to maybe make use of the larger pipe diameter. Okay, so we got a much smaller pressure drop when we did this calculation using the larger pipe diameter of 20 nominal millimeter, but at least this result is not wasteful with energy. Now we need to select a control valve, and since 20 millimeter is the smallest that we can choose, we have no other option but to select this. If we went with a nominal pipe diameter of 15 millimeter, we would still have to make do with this 20 millimeter option. So let's move on and determine that for the single port type 20 millimeter nominal diameter control valve, we obtain a coefficient for this control valve of 5.4. Now we can proceed with checking the rest of the results. Now in industry you have a lot of available options for control valves. You don't have to use this piping handbook. Typically the coefficient will be specified for the particular type of control valve. So if you're sitting at your desk one day in industry and you need to install a control valve, you would likely get a manual or a list of specifications from the supplier before you go out and buy or order a control valve. You would first do these calculations and make very certain that you buy the right one. And in general you would end up buying more than one, because remember, you might have to do maintenance on a control valve and you need a second backup or even a third backup. A third backup would be maybe more costly for you, so usually there are control valves on standby at the workshop or at the warehouse, so just keep that in mind. You don't want to order a wrong control valve and then have to send it back to the supplier after you've installed it. It's just a very costly procedure. Now we can proceed to check the rest of the rules. Now firstly, rule 1D is automatically satisfied and the pressure drop across the control valve is calculated to be 483 kilopascal. Now we check the fraction of the total flow area of the control valve, which is f of x, and then using the design equation at the designed flow rate, the fraction can be then determined, and we determine it as being 0.03, which is 3% open. So this control valve has to be 97% in the closed position. So this is pretty ridiculous, and this design will simply not work. This is a very good example that demonstrates how these checks and balances are used in the proper design of a system that uses a control valve. And sometimes you may find that the system itself is not well designed to begin with. It is likely that the flow rate of 1.2 meter cube per hour is simply too small, but this is what is required for the process operating conditions. The other options therefore would be to consider using a smaller pipe diameter, or finding a much smaller control valve that can be operated in a more open position, or else the process specifications would have to be changed in otherwise. And with this we end off the example.